So for number 46, we want to see if this sequence over here converges. And now a sequence AN converges if it tends to a specific limit as n goes to infinity. So what we're going to do here is we're going to take this limit. So the limit as n approaches infinity of 2 to the negative n cosine n pi. And we're going to see if this spits out a defined number. And I'm just going to clean this up a little bit. And the first thing that I'm going to do is I'm going to take this negative n and I'm going to put it on the bottom just so that we have a quotient, which is nice whenever we're dealing with infinity. So we'll go 1 over 2 to the power of n, and all of this times cosine n pi. Okay. So let's see what happens to each of these individually. So the limit as n approaches infinity of 1 over 2n, the reason that we express this as a quotient was because now we can say, okay, that is 1 divided by 2 to the power of infinity, that's infinity. So 1 divided by infinity, it tends to 0, right? Anything divided by a very large finite number divided by a very large number, this tends to 0. Now, what about the limit as n approaches infinity of cosine n pi? What happens here? Well, cosine n pi, so when we, it's going to just evaluate the multiples of pi that are natural numbers. So it's going to evaluate cosine of pi, cosine of 2 pi, cosine of 3 pi, and so on and so forth. And now, multiples of pi and the cosine are basically going to oscillate. They're going to oscillate between 1 and negative 1, right? So cosine of pi is going to be negative 1, cosine of 2 pi is going to be 1, cosine of 3 pi is going to be negative 1, cosine of 4 pi is going to be 1, and so on. And so we can see here that this just oscillates between negative 1 and positive 1, negative 1 and positive 1. So actually this has no limit, right? It does not converge. So how can we talk about a limit when part of this sequence does not have a limit? Well, what we're going to do here, so we're going to say, okay, cosine n pi divided by 2n. So the top part doesn't have a limit, but the bottom part does, right? And so what we're going to do here is we're going to use something called the squeeze or the sandwich theorem. And basically this theorem, I'm going to illustrate it using functions, but it's just as valid using sequences. So suppose that I have over here at x is equal to a, and there's a limit L, right? And suppose that I have a function here, maybe you can call this f of x, and we can see here that as x approaches a, it has a limit L, right? And then we have another function here that is g of x, and it also has that same limit as x approaches a, L. And we can see here that g of x is always less than or equal to f of x. Now, suppose that we also have this other function that's between them. So it's less than f of x, but greater than g of x, and it's between them. So what we have here is that f of x is greater than or equal to h of x, which is greater than or equal to g of x. And this basically means, hey, if h of x is sandwiched between these two functions, and if the limit of these two functions, the upper and the lower, as they approach a, if that limit is L, then it means that the middle function, because it was sandwiched, the limit must also be L, right? It must also have the same limit. And so this idea is also valid for sequences. And so what we're going to do here is, let me just move this around. We're going to sandwich this sequence between two other sequences that have a defined limit. So we're going to say that this is definitely less than or equal to 1 over 2n, and the reason that it's less than or equal to 1 over 2n is because cosine n pi, it doesn't ever get bigger than 1. It's at most 1, right? And then we can say that this is definitely equal to or bigger than negative 1 over 2n, because again, cosine n pi, it never gets smaller than negative 1. So because cosine n pi is bounded between 1 and negative 1, this inequality here is always true, right? And then we're going to say, okay, the limit, since we've kind of set this up in this sandwiched idea here, where cosine n pi over 2n, that is the one in the middle, and then 1 over 2 to the power of n, that's the upper one, and negative 1 over 2n is the lower one. We've set this up in a nice sandwiched way, and now we're going to take the limit of the outer sequences, right? So we're going to say the limit as n approaches infinity of 1 over 2n. Well, we've already shown that this is just 0, right? It's 1 divided by a very large number. And what about the limit as n approaches infinity of negative 1 over 2 to the power of n? Well, it's negative 1 divided by 2 to the power of infinity. So still negative 1 divided by infinity. It doesn't matter that it's negative. It's still going to tend to 0, because any finite number divided by something really large is going to tend to 0. So we can say, okay, because cosine n pi over 2n is bounded between these two sequences, and because the limit of these two sequences is equal to 0, then this limit must also be equal to 0 by the squeeze theorem. And so if this limit is equal to 0, we can say that, and let me remove this here. And so we can say that an, it tends to 0 as n gets large, so an converges because it does have a limit, right? It does tend to 0. And so we have proved this using the squeeze theorem.